How can huge amounts of satellite data be used for social good? The answer lies in human agent collectives. I will demonstrate through several applications how human agent collectives can provide solutions to practical problems in disaster management and environmental protection. This work is in collaboration with my team, Olga, my postdoc, who now has a faculty position at Bath University, her husband Daniel, who is a postdoc working on several of the projects I will talk about shortly, and my PhD student, Tommy Lees, who is a climatologist working at the interface of weather impact and machine learning. First, something about me. I lead research group in machine learning in the engineering science department at Oxford University. My group focuses on developing machine learning methods for solving problems in disaster management and environmental protection. We work closely with NGOs and industry to identify gaps in machine learning capability and ensure our methods have some significant impact in the real world. Our participatory design approach to research ensures that we are addressing pertinent problems for practitioners and policymakers. I'm also a fellow at the Alan Turing Institute, the UK's National Institute for Data Science and Artificial Intelligence, where I'm also a group leader in the Lloyd's Register Foundation funded Digital Centric Engineering Programme. I'm also a research in residence at the Satellite Applications Catapult, which I call the SAC. I've been involved in several SAC-led projects, which I will draw your attention to throughout this presentation. I am seeking to extend my network of project stakeholders and collaborators for the next round of funding, anticipating projects beginning around June 2021, though we will need to start discussing the aims of these projects much sooner than that. For the rest of this talk, I will present a brief summary of research and delivery projects we are undertaking that demonstrate what we do and how we collaborate with different kinds of organisations. Despite huge advances in machine learning recently, especially in deep learning on neural networks, there's still significant challenges to getting the technology to work out of the box. Improving the technology so it exploits data appropriately for each application requires careful algorithm design as well as problem-specific training data. For many use cases, good quality human-labeled data is crucial to train neural networks, and obtaining this data from expert labelers in a timely manner can be costly. However, well-managed cohorts of citizen scientists, such as you and me, can often provide high-quality data annotations at a fraction of the cost. Introducing transferable computer algorithms, or agents, into the mix alongside human labelers, thus forming human agent collectives, has the potential to significantly scale data analytics and provide actionable intelligence from huge datasets. So our research question is, how can human agent collectives turn satellite imagery into actionable intelligence, cost-effectively, timely and accurately, to help practitioners and policy decision makers? Answers to these questions require advances in methods at the interface of Bayesian and deep learning, the integration of machine learning into crowdsourcing platforms, and scalable algorithms that combine sometimes unstructured, huge, and different but complementary datasets. Our research aims to develop these methods. Here's an example of what I mean. Hurricanes Irma and Maria struck the Caribbean islands in 2017. Their destructive power was immense, directly causing 3,300 deaths and over $282 billion worth of infrastructure damage. Working with satellite imagery providers Planet and Maxar and the citizen science platform Zooniverse, we mapped damage in 16 islands worst affected by the hurricanes. The actionable information request came from Rescue Global, a not-for-profit NGO that provides situation awareness to disaster relief organisations such as the UN. Citizen scientists compared pre- and post-disaster satellite imagery, and we used machine learning to turn their annotations into heat maps. Heat maps are colour-coded maps of damage overlaid onto the satellite imagery. These maps were used by over 60 NGOs, UN OCHA, FEMA, to help them plan their disaster aid efforts. We invoked this pipeline again in 2019 following requests by Rescue Global and 24 Commando Royal Engineers in response to Hurricane Dorian. Lifting the lid on the technology a bit. Zooniverse is a web-based tool that citizen scientists can use to annotate satellite imagery from the comfort of their own homes. Machine learning is used in two separate places in the pipeline. Machine learning aggregates the citizen scientist labels provided by Zooniverse, removing individual volunteer bias and labeling error using a Bayesian algorithm that captures the wisdom of the crowd. It's important to note that we do not require ground truth data to calibrate the citizen scientist responses. Also, the citizen scientists are tasked with labeling only a subset of the satellite imagery, and a neural network labels the rest of the imagery in parallel with the crowd. The aggregated human agent labels are used to retrain the neural network, and this process continues until all the satellite imagery is sufficiently labelled. The pipeline includes methods for intelligent task allocation, which tells Zooniverse what imagery the citizen scientist should label next, to provide the greatest information gain and optimize labeling efficiency. The system provides a fast and human resource efficient method for labeling vast amounts of imagery. Our earlier work focused on mapping the general damage at district level. In Europe's paper is available online if you'd like some further detail of this earlier work. Ongoing work, funded by the FTSC and in collaboration with Lancaster University, is underway to improve this pipeline, using point crowd labels and region-based convolutional neural networks to identify the extent and degree of damage of individual buildings. In collaboration with us, the SAC has exploited our human agent collective technology through an Innovate UK knowledge transfer project. Please get in touch with us if you're also interested in exploiting or helping to further develop this work. Most people think that earthquakes only occur when the plates rub past each other. But many earthquakes occur in continental interiors, hundreds or thousands of kilometres from the plate boundaries. About 2/3 of earthquake-related deaths in the past 120 years have been caused by these intracontinental earthquakes. The risk to life of these earthquakes is increasing rapidly as large populations migrate into vulnerable megacities. It is estimated that between 1 and 2 billion people are exposed to this risk. The most depressing problem is that most of the faults that cause these deaths are not detected until after they have generated a devastating earthquake. Our work is aimed at mitigating disasters by mapping these faults globally. In collaboration with Oxford Earth Sciences Department, we are adapting a form of neural network, called the UNet, to map these hazards. The approach fuses heterogeneous data maps, including red, green, blue Landsat optical imagery, near-infrared band, and derived slope and topography roughness to highlight fault lines via overlays on satellite imagery. In the example on the slide, red indicates high probability of a seismic fault and blue, low probability. As you can see, the fault lines are clearly identified. This is ongoing work. You may remember from last year the collapse of the iron ore tailings dam in Brumadinho, Brazil. This dam collapse claimed 248 lives and, unfortunately, was not a unique event. Just over 2 tailings dam collapses occur on average worldwide every year. Many of the Brazilian dams are not known by the Brazilian authorities. We've been working with the Brazilian National Audit Office to map tailings dams in 2 areas of interest in Brazil, covering in total 237,000 square kilometres. A representative from the Brazilian National Audit Office, who is also a professor of computer science at the Catholic University of Brazil, studied at Oxford as a visitor for 5 months. During this time he learned about neural network analysis of satellite imagery, and we worked together to transfer the algorithm we use for BOMA detection, which I'll describe shortly, to dam detection and also dam classification. Dams were classified according to their potential environmental impact as high impact waste products such as lead, iron, phosphate, nickel, and low impact waste such as sand, gravel and clay. As the confusion matrices show, we successfully mapped and classified a large proportion of the dams in our 2 areas of interest. Furthermore, we identified and mapped 263 tailings dams that did not have official mining concession in these areas of interest. For further information, a preprint of our work is available on arXiv. Land use change is having a devastating impact on wildlife. We have two projects with Save the Elephants and the Department of Zoology at Oxford University aimed at enabling the wide area delivery of information to conservation organisations to improve their understanding of the impact that human infrastructure has on animal behaviour and survival. Save the Elephants works with the Kenya Wildlife Service, the government department equivalent to DEFRA, and Samburu and Isiolo local governments to drive efforts in conservation. Save the Elephants and their government partners want to know what land should be set aside for wildlife corridors that has minimal disruption on the local human population, especially farmers. Currently, Save the Elephants undertakes laborious manual processing of high-resolution optical satellite imagery to identify and label human infrastructure over huge areas of interest. This manual process is costly, slow, prone to error and incomplete, and does not provide information in a timely manner. One of our projects, funded by Google X and an Oxford University Internal Impact Acceleration Award, uses our human agent collective technology to map farmsteads, called bomas, from the high-resolution satellite imagery. Can you spot the bomas in the satellite imagery in the left column? Some are obvious, some are less so. The two masks in the central column show the locations of the actual bomas. This is the hand-labelled data provided to us by Save the Elephants. The two masks in the right column are the bomas discovered by our machine learning tool. We are working to improve the technology to reduce the false positive rate. Although this project focuses on boma detection, classification, our approach is capable of mapping a wide range of different infrastructure types. We have started to exploit this technology to identify cement plants globally as part of a spatial finance initiative project funded by the Children's Investment Foundations Fund, in collaboration with the SAC, Alan Turing Institute, Australia, and the Smith School of Enterprise and the Environment at Oxford University. Reliable, accurate and up-to-date data on wildlife numbers is essential to monitor population fluctuations and identify causes of decline, such as human conflict or habitat loss. Various methods are used for conducting population counts, such as line transect surveys, dung and track counts, bioacoustic monitoring, camera trap and aerial surveys, but these can be logistically complicated, slow and prone to double counting. The second project we have with Save the Elephants is aimed at detecting and counting elephants in satellite imagery. Again, can you spot the elephants in this imagery? The red boxes are expert-labelled elephants and the green boxes are the machine-labelled elephants, obtained using a region-based convolutional neural network. The approach is accurate, as demonstrated by a relatively high F2 score. We asked citizen scientists to label the imagery and found that our neural network has a similar accuracy to the citizen science labellers. Two papers are available that detail the work. The Journal of Southern Africa paper is online. Please contact us if you're interested in our recently submitted work to Methods in Ecology and Ecology. This project focuses on the development of time series prediction algorithms for large datasets. Agricultural drought is a significant global problem, accounting for $29 billion losses to the developing world between 2005 and 2015. Adapting an LSTM, that's a long short-term memory neural network, originally used for rainfall runoff modelling, we predict the Vegetation Health Index 1 month ahead at roughly 30-kilometre resolution for the whole of Kenya. This work was undertaken by my student Thomas Lees as part of his PhD in collaboration with Oxford's Department of Geography. Tommy is investigating the efficacy of entity-aware LSTMs as a model of the impact hydrological and meteorological processes have on vegetation health. Predictors include evapotranspiration and soil moisture, precipitation and potential evaporation and temperature, soil type and topography. Note Tommy's purely data-driven approach is as accurate as the state-of-the-art physical model-based approach that is in operational use by the Kenyan National Drought Management Authority. For further details, please see our ICLR paper. Finally, I should mention 3 other projects in disaster management and environmental protection we are or have undertaken recently. Reading from left to right, we contributed to an online tool, Marine Watch, developed by Risk Aware under the SAC-led UK Space Agency funded project ESOS. For this tool, we developed a Bayesian machine learning approach that efficiently identifies the source of maritime oil pollution, as well as estimating the oil release profile from satellite imagery of the surface oil. The solution reduces the computational cost of searching through a huge space of possible oil release profiles to rank the most likely culprits. We are working with local resilience forums, the MOD, and with support of the Joint Biosecurity Centre to now cast local surges of COVID-19 infection rates. Our approach uses machine learning to link mobility data from mobile phones to disease case counts via a combination of SEIR compartmental modelling and data-driven models. Finally, we are working with the Department of Plant Sciences to exploit satellite imagery to map forest quality in Malaysian Borneo. Plant Sciences have developed a citizen science app that is deployed on the ground to measure forest quality at select locations. It takes several minutes to complete a survey at each location using this app, and wide area surveys would be very costly. We are investigating the use of satellite data as a proxy for wide area forest quality mapping. We have a small grant for a prototype study and are at the early stages of writing a proposal for further funding. If you would like to be involved in this proposal, or would like to talk to us about any other machine learning applications in disaster management or environmental protection, please get in touch.